Hello, folks. There we go. Ooh, I'm too loud. Okay, I'm going to review some of the main concepts we talked about last time. I changed notation near the end of the hour on one of the inequalities, the Chebyshev inequality, and that seems to have caused confusion. It turns out the expression I wrote first was correct, and the expression I changed it to was also correct. But there was a symbol problem, and I'm going to fix that before we move on to the Polster problem and then the central limit theorem for the rest of the hour. And then if there's time at the end, I'll talk about conditional densities. All right, so what did we do last time? We went through several stops on our train ride. The first stop was the tail probability theorem, so this the formula. So this is a review. Tail probability formula. It said that, and it had two flavors, one for discrete random variables and one for continuous random variables. So if the discrete version is that if x takes on non-negative integer values for all sample points, so it's a non-negative random variable. So that basically is a fancy way of saying x is a non-negative random variable. Then the expected value of x, which by definition we know is the sum over all k times pk, whoops, I need the random variable there. This summation is going to equal the sum from 0 to infinity of the probability that x is strictly greater than k. And of course, the kernel of this sum is the complementary CDF. This is the complementary CDF, the probability that a random variable takes on values greater than a certain threshold. Its continuous counterpart was the same. We didn't derive this. I derived it for the integer valued non-negative random variables. So I actually cheated. I proved it for the simplest possible case. The continuous version says, well, we got it just from the summation formula. Instead of the sum, I have an integral. The sum goes from 0 to infinity, so I integrate from 0 to infinity, and I have this random variable that has a complementary CDF. So there you go. That's the formula. And looking at the CDF of a non-negative, so this is now a continuous random variable that is non-negative. So that's the premise throughout. Now, if I plot the complementary CDF for a random variable that's non-negative, all the probability is sitting to the right of the number 0. So this function starts at 1 and decays. Okay? It's non-increasing as we go toward plus infinity, because less and less probability is sitting on the right tail of the corresponding PDF. And then, from here, we looked at a particular value A and its corresponding complementary CDF, and we looked at that area. So when I look at that area, A times fxc of A, that area is clearly less than or equal to the total area under the complementary CDF curve. So I can write this. Right? And what's the right-hand side based on what we saw in station 1? It's what? Everybody. Expected. That's not everybody. Come on. Expected value. Thank you. And so what this says is that the complementary CDF is less than or equal to the expected value of x divided by a. But then the complementary CDF is simply the probability that x is greater than a. And that says, that translates to this inequality. And this inequality we called what? Markov. All right. Then we started writing toward another station, and we said, okay, if for some arbitrary random variable x that is non-negative, this is true, then what if I define a random variable y to be x minus the mean of x squared? Well, if the random variable y is the square of some other random variable, here that random variable is x minus the mean of x squared, clearly y is non-negative, so I can apply Markov. And what happens when I apply Markov? Well, this says that the probability that y is greater than a. By the way, I can put, for most random variables of interest, I can put an equality here without altering the balance in the universe. Unless the continuous random variable has a positive probability of taking on the exact value a, I don't have an issue putting an equality sign. If a is not one of those points where the continuous random variable takes that value with a non-zero probability, I'm okay putting that inequality. So, or the equality here. So I'm going to do that for our typical run-of-the-mill vanilla random variables. So Markov's inequality says that, whoops, that's not an expected value. That's a probability. The probability that y is greater than or equal to a is less than or equal to the expected value of y over a. But the expected value of y, given the way I've defined y, is simply the expected value of x minus e of x squared. And then the denominator is a. And you recognize the numerator as variance of x. Okay? So that's where we are. Now, this is how I wrote the, actually let's massage the left-hand side and write y explicitly. So y is x minus e of x squared greater than or equal to a is less than or equal to the variance of x over a. Okay? Near the end of the hour, I changed this a to a squared, which is fine. A is some positive quantity. There's nothing sacred about a. I can instead of writing a, I can write a squared. But that was clumsy. So what I'm going to do is first note that a is greater than 0. If a is equal to 0, the whole exercise is irrelevant. The point is moot. We don't care about this inequality. And if a is negative, then the left-hand side is simply 1. So if a is 0 or negative, the left-hand side is 1. The probability that non-negative quantity is non-negative is 1. So it's kind of foolish to harp on that. So the interesting cases are when a, that threshold, is a strictly positive quantity. Well, if a is positive, then we can let a be the square of some other positive quantity for some epsilon greater than 0. Okay? That's what I should have done near the end of the lecture. So, any positive quantity can be written as the square of some other positive quantity. Okay? There's no magic there. So now my inequality is the probability of x minus e of x squared is greater than or equal to epsilon squared. And on the right-hand side, wherever I see an A, I replace it with epsilon squared. Now, so hopefully this has ameliorated some of the confusion near the end of the hour. Now what I'm going to do is talk to you about the event x minus e of x quantity squared being greater than or equal to epsilon squared, and the event absolute value of x minus e of x greater than or equal to epsilon. How are these two events related? They're what? They're the same. In other words, this holds on the left if and only if the right inequality holds. So if that's true, then the probability that x minus the expected value of x is squared is greater than or equal to epsilon squared is the same as the probability. Wait, I haven't written this r here. Probability that x minus e of x absolute value is greater than or equal to epsilon. There is a nice interpretation to the probability expression on the right. I am looking at the likelihood that the non-negative random variable x is deviating from its mean by more than a certain amount. And that amount is the distance. It doesn't matter if it goes to the left of that mean or to the right of that mean. I am looking at the probability that x is outside of some distance from its mean. Chebyshev's inequality says that the probability that x deviates from its mean by more than a certain amount is less than or equal to sigma x squared over what? This is where you've got to be careful. I wrote equivalences on the left-hand side. Did I touch anything on the right side of the inequality? So what should I put here? Epsilon or epsilon squared? Epsilon squared. It's the probability on the left-hand side that I found an equivalent for. The right-hand side stays where it is. I'm not changing variables anymore. Okay, so this is a cleaner form of Chebyshev's inequality. Now, the interpretation of this inequality is important. If the spread or the variance of a random variable is small, it means that the probability that it deviates away from its center of mass is also small. Okay? So there's a bound on how much a random variable can deviate from its mean, and that bound is given by what's on the right-hand side by Chebyshev's inequality. It's not a tight bound, and when we solve the Polster problem using Chebyshev's inequality, you'll see that you'll notice that the bound is not tight. Okay, so that was that. Then we got to, what was our next stop? The weak law of large numbers, correct? So that now I'm working my way up to solving that pole problem. So here we talk about the weak law of large numbers. So I take a bunch of random variables that are independent and identically distributed. These random variables have mean e of x and variance sigma x squared. I average these random variables. I take a simple arithmetic average. And you told me last time what the mean was for this sample mean. So this is called the sample mean. I can also write this as Sn over n, where Sn, so this is the sample mean. Sn is simply the sum of the random variables. We won't have much occasion to use that. It may occasionally show up in some of the expressions, but by and large we'll stick with Mn. So what's the expected value of Mn? How do I figure it out? What happens to this n in the denominator? Take it out. And does it stay as n or n squared? This is some 1 over n. Think of this n in the denominator as 1 over n times some random variable. That random variable happens to be s of n. Okay, so when I take the expected value of Mn, isn't it, here, let's write it this way. Isn't it just 1 over n times e of Sn? Yes or no? Okay. And then I have the expected value of a sum, and that's the sum of the expected value. So what do I get in the numerator? Given that they're all identically distributed. N times the expected value of x, and I have an n in the denominator, and this is e of x. We showed this last time, and we said that the expected value of this mean is the actual mean, which means Mn is unbiased with respect to the true mean. And the variance of Mn is what? If we talk in terms of the sum. So I've got some random variable Sn in the numerator, some constant 1 over n multiplying it. So what's the variance? What happens to constant multipliers when you take the variance? Square it. This is where the square happens. I tripped some of you when I asked about the square in the previous one. So make sure you get comfortable with that. You don't want to be worried about these kinds of things on an exam setting. So it's 1 over n squared times the variance of s. So what's the variance of a sum of independent random variables? Sum of the variances. And they're all identically distributed, and each term has variance sigma x squared. So I have an n squared in the denominator, and I have an n sigma x squared. So the variance of my sample mean is this. What happens to this variance as n goes to infinity? Approaches 0. So if you were to guess something about the behavior of the probability law governing the sample mean, what happens to the probability law? Does it get wider? Does it get narrower? What happens to it? It gets narrower because the spread is getting tinier and tinier. Okay. And this is where we get the weak law of large numbers from. So the weak law of large numbers. You don't have to worry about the fact that the word weak here. I have to say it here because my colleagues and I have OCD about these things, and we want to be precise at certain points. There is a strong law of large numbers which makes a stronger statement about how the sample mean behaves. But we don't talk about that in this class. I think they might talk about it in E126. So the weak law of large numbers says if you have a bunch of random variables xn that are IID, each has a mean e of x and variance sigma x squared, then the probability that Mn moves away from the true mean, in other words, the sample mean moves away from the true mean, which is what? This is less than or equal to what? What does Chebyshev's inequality tell you? Huh? So it's the variance of what? Xi or Mn? Mn. It's less than or equal to the variance of Mn over epsilon squared. And we found the variance of Mn to be right here. Sigma x squared over n. And I've got this epsilon squared here. Okay? So, the weak law of large numbers says what you can see very clearly from the right-hand side expression. That the limit as n goes to infinity of the probability that Mn deviates away from its true mean is less than or equal to the limit of sigma x squared over n epsilon squared, and this is equal to what? 0. So this is the statement of the weak law of large numbers. The probability that Mn moves away from its true mean by any arbitrary positive amount approaches 0 as n goes to infinity. So this is sample mean converges in, so I'm going to put that in quote, probability to the true mean as the sample size n increases. So there's this notion of convergence in probability. You might remember from calculus there were a whole bunch of notions of convergence. There are different types of convergence. This is one type of convergence that we talk about here. We're not going to go into any of the esoterics of convergence and this type of convergence and that type of convergence. The only thing I'm going to say is that the reason we call this a weak law of large numbers is that convergence in probability is a weak form of convergence. For example, so let me just state that. Convergence in probability is a weak form of convergence. For example, it says nothing about the mean or variance. What do I mean by that? Let's do an example. So here's an example. I have a sequence of Bernoulli random variables. So let y1, y2, y3 be such that the probability law for the nth one follows this Bernoulli setup. It takes on the value 0 with probability 1 minus 1 over n. And with probability 1 over n, it takes on the value n squared. So I define a sequence of random variables that behave in this way. Are they identically distributed? Tell your neighbor if they're identically distributed. This is for n equals 1, 2, and so on. Is the probability law governing random variable capital Y1 the same as the probability law governing the random variable capital Y2, for example? Yes or no? Rohan.
No, because based on just from the construction of these random variables, you've parameterized the distributions on on the subscript. So y sub 100 will have a much larger spread, sort of, than y
Okay.
1.
So let's just stick with 1 and 2. The left lollipop, does that move with n? I'm not saying if its height changes. The height obviously changes. But does it move? No. So for every one of these random variables, each one of these random variables has, with probability 1 minus the inverse of its index, it's going to take on the value 0. But what happens to the right lollipop?
It'll move.
It'll move. So when n equals 1, the probability, so show me how to draw the probability mass function for y1.
So
At 0, it's got height what?
0.
Huh?
It's got a height of 0.
0. Oh. Let's do 2 and 3 then. That's not going to be very helpful. So let's do 2. y2. Okay? There's a lollipop at 0 of height
1/2.
1/2, yeah. And then the other lollipop is where?
4.
Actually, we can also do the 1. That's not bad. So, but where's the next lollipop?
4.
At 4. This is 2 squared. And the height is?
1/2.
1/2. Okay, now what about 1?
There's only one lollipop, and it's at 1 with the height
It's
of
at 1. At 1 squared. And it's got height 1. And then if you go to 3, there's a lollipop at 0, and the other lollipop will be at what?
9.
9. So as you can see, once I start indexing up, the lollipop at 0 starts getting larger or smaller?
Larger.
Larger, until it approaches 1 as n goes to infinity. And the lollipop on the right keeps going which direction?
To the right.
To the right. Farther and farther. Faster and faster, in fact, because it's doing it on a square basis. But even though it's going to the right faster and faster, what's happening to its height?
It's shrinking.
It's decreasing. But notice the height is decreasing on the order of 1/n, but the lollipop is moving on the order of n squared. So let's see what that does to the mean. You tell me, for this Bernoulli random variable, what the mean is, and as an intermediate step through the variance, tell me what the variance is. What the second moment is. So figure all of these 3 out. Go. Talk to each other. This is no different from the Bernoullis that you've been studying. It's just that there is a dependence on n. There's nothing else going on. You still have 2 lollipops. Okay, what do we have for the expected value of y, folks? Does this lollipop contribute? Huh? No, because it corresponds to the value 0. So the only lollipop that contributes is this one. This is the only lollipop that contributes. This guy here. So, to figure out there's only one term then in this summation. So what do I put? What's y of n there? N squared times the probability, which is 1 over n. So this is n. So notice the mean of this sequence of random variables keeps increasing. As n goes to infinity, you're looking at an infinite mean random variable. What about the square of the random variable? Again, there's a single lollipop. For a particular n, the square of the random variable is what? N squared to n squared, and then the probability of that is 1 over n. So I've got n4 times 1 over n, I've got n cubed. And now the variance is what? Expected value of? What's the y squared minus expected value of y squared minus square of the expected value. So the second moment we figured out. The first moment we figured out, we square that, and we've got n squared times n minus 1. This also blows up as n goes to infinity, and this blows up as n goes to infinity. What happens to the probability that y of n minus 0 is greater than a certain amount? Y of n minus 0 is greater than or equal to a certain amount as I take this to infinity. This is the limit of what? What is that probability? Huh? What? What does this probability translate to in terms of that diagram? How do I measure this probability? How do I figure out what the exact expression for that probability is? Let me rephrase that. This is problematic. The probability, I'm asking the probability that y is greater than 0. What am I summing? How many lollipops am I summing? The second one. Yeah. That probability is precisely 1 over n. And that goes to 0 as n goes to infinity. So even though the sequence converges in probability to the number 0, its spread blows up as n goes to infinity. That's why convergence in probabilities is called a weak form of convergence. But the weak law of large numbers is enough for us. Whoa. Take it easy. To move forward. All right. So, let's see if we can take a stab at the pollster problem based on what we have studied so far. So let's do the pollster problem. Pollster problem. Yeah. Why is it 1 over n? So when you look at the nth random variable, I'm asking what's the probability that it's positive? It can only take on two values, 0 and n squared. Right? And only one of those corresponds to a positive value, the one at n squared. So I just look at the probability at that point, which is 1 over n. So the event is that y of n is positive, and I look at all the values of n for which the random variable is positive. There's only one. That happens at n squared, and the probability of that is 1 over n. Let me get rid of some of these highlights that I drew. Right? Okay. So remember the pollster problem. Let's restate that. We want to determine, we can't determine. We want to estimate the true fraction mu of U.S. voters who believe marijuana should be legalized. You can replace this with whatever you want. If you don't like talking marijuana, say you want to estimate the fraction of the U.S. voter population or the population in general that believes in God. I don't know, pick any Bernoulli. Yeah. Yeah, so there are statistics about the sequence of random variables that are not tightened as a result of the probability narrowing down. Actually, the probability is not narrowing down. The probability of it being greater than 0 is going to 0. So even though all the probability is starting to amass in the lollipop at the origin, the spread is increasing. Yeah. Oh, sorry. This is the variance of y. Thank you for that correction. That's the variance of y. Okay. So, here's what I want to do. The question is, what is the smallest sample size? I'm a pollster. I want to figure out how many people I've got to ask this question of. What is the smallest sample size n such that, and you'll often find me write such that in this way, we are at least 95% confident that our estimate, what is our estimate? Well, I'll write it up in a moment. Is within 1% of the actual fraction mu. 1% means 0.01 here. So we want to estimate mu with a plus minus 0.01 accuracy. And we want to, so in any poll, if you notice, when you listen to political polls or other polls, there are always two parameters that are involved. What's the accuracy? Plus minus 3%, plus minus 2%, what have you. And the confidence with which you have estimated that. Okay? So here, what we're measuring is for the ith voter. If the ith voter believes that marijuana should be legalized, then we have an indicator random variable for it, which takes on the value 1. Otherwise, and that happens with probability mu, because mu is the actual fraction of the population that believes marijuana should be legalized. So if I take a randomly selected person from the population with probability mu, I'm going to get an answer of 1. And with probability 1 minus mu, I'm going to get an answer of 0. Now I want to figure out how many of these people I'm going to sample and average. So to get the estimate of that fraction mu, I'm going to ask n people, add up all their values. For every person that said yes, I get a 1. So I add up all those values and divide by the sample size. And this is an estimate of mu. So the sample mean becomes our estimate of mu Is everybody here? Is the setup clear? Okay. Now, so we're trying to figure out the minimum n, determine the minimum n such that the probability that the estimate is away from the mean by more than what? So it is within 1% is less than or equal to what? Oh, I'm sorry, is greater than or equal to what? So let me label these things. It's very important that you be able to translate the specification for the pole into an inequality. So we're looking for a probability because we're talking about a confidence. The probability that the sample mean is away from the true mean and what did we say here? Is within 1%. So that means it's less than or equal to 0.01. And we want to, so this is the accuracy. Accuracy. And this should be, we want to be able to say this with what confidence? At least what? Huh? 95%. Yeah. The actual total fraction. 1. Yeah. Okay. Now, this inequality, so please talk to your neighbor for about 30 seconds or so and make sure that you can explain to each other how I translated the specification for this pole into this inequality. And then we have to talk about how to convert this inequality into the form that the Chebyshev inequality is in. The Chebyshev inequality doesn't have these inequalities in the direction that we have here. Okay? Go for it. And I'll turn this into a strict inequality just so that we don't get bogged down over. I want my accuracy to be within 1%. Yeah. All our scalings are between 0 and 1. Mu is some number between 0 and 1, and my 1% is a number between 0 and 1. Yeah, actually maybe this is what's confusing you. Within 1%. No, actually that's actual mu. Yeah, 1% is our accuracy. Mu is itself a number between 0 and 1, right? Yeah. Okay. So, now these inequalities are not in the direction I want. I want to convert them into inequalities that I know how to apply the Chebyshev inequality to. So, what can I do to this to change it into some probability that Mn minus mu is greater than or equal to 0.01? How do I go from here to here? How are these two probabilities related? They're complements. So I have this is equal to 1 minus that. And I want this to be greater than or equal to 0.95. And I take the 0.95 to the other side, so I have 1 minus 0.95. And I take the probability to the other side, and then I reverse again. Mn minus mu is greater than or equal to Wait, what happened to that? It just disappeared on its own. Is greater than or equal to 0.01. And so what this means is I'm looking to figure out what it takes so that the probability of me having a greater than or equal to 1% error is less than or equal to What is going on here? Okay, is there an undo here? Undo. What? There we go. Is less than or probability Mn minus mu is less than, is greater than or equal to 0.01 is 0.95. Okay. Please behave. Alright, now this is in the form that Chebyshev's inequality can help us with. What does Chebyshev's inequality say about this probability on the left-hand side? What is going on here? Let's check this and something else here. What does Chebyshev say? That this probability is less than or equal to what? Variance of what? Mn over, what's my epsilon here? Isn't this my epsilon? Yes or no? Okay. So here I have what in the denominator? Epsilon squared. Yeah, 0.01 squared. 0.01 squared. So if this is the upper bound, and let's put in the values. What was the variance of Mn? Can you go back in your notes? What was the variance of Mn? This was the variance of Mn, no? Sigma x squared over n. Sigma x squared over n, and I've got this 0.01. Can we make this 0.01 just 10 to the minus 4 and be done with it? N times 10 to the minus 4. Okay, so Chebyshev's inequality gives us an upper bound. And if we make this upper bound less than or equal to 0.05, we're golden. Correct? So the probability of being off from the true value by more than 1% is bounded, according to Chebyshev's inequality, by this quantity. So that's an upper bound on the probability. If I make sure that that is less than 0.05, I'm done. Right? What is sigma x squared? Remember, they're all identically distributed. This is your run-of-the-mill Bernoulli. What's the mean? Quickly! Mu. And what's the variance? Mu times 1 minus mu. We've done this a few times already. Okay, so what I have here is that mu times 1 minus mu over n times 10 to the minus 4 is less than or equal to 0.05. The inequality you want to get at the end for n, is it supposed to be n greater than or equal to some threshold magical number, or n less than some magical number? Greater than, because you got to go poll more and more people to get better and better accuracy. So this is hopeful. This is a promising inequality, because when I try to solve for n, I get n greater than or equal to something. All right. You know what? I'm going to keep this as sigma x squared for now because of clutter. I'll pull in the m times m minus 1 in a different way. So what this means is that n times 10 to the minus 4 over sigma x squared is greater than or equal to, if this is 5 times 10 to the minus 2, what do I have on the right hand side? 1 over that, no? And then I have n is greater than or equal to sigma x squared over 5 times 10 to the minus 2. Help me out here, people. What should I write? Times 10 to the 4. Okay? But we have a problem. Our problem is this. This is our snag. Snag. Sigma x squared is mu times 1 minus mu, and we don't know mu. What should I do? Assume the worst. Always works. Assume the worst. Assume. That was a brilliant way of putting it. Assume the worst. Notice, if I assume the worst, that means I assume the maximum possible value sigma x squared can take. And that gives me a bound on the right-hand side, which makes my n bigger. Right? N has to be bigger than something that's proportional to sigma x squared. So if I take the worst possible sigma x squared, I'm good. I'm safe. Is everybody with us? Yes? All right. So now the question is, what is the worst? What is the worst sigma x squared? The answer is it's maximum or minimum? It's maximum. And we've already answered that question in a previous lecture. So sigma x squared as a function of mu is mu times 1 minus mu. And that goes from 0 to 1. And its peak is at 1/2, which produces the worst mu, which is 1/4. So worst sigma x squared is equal to the max sigma x squared, maximized over mu, and it's 1/4. Okay. Wow. We're making progress here. So n is greater than or equal to 1/4 times 5, 10 to the 2 times 10 to the 4. Can somebody give me that number? What does that work out to? 50,000. Did I blow your ears away? Good. I want to make sure everybody's awake. Now, how many polls have you seen where they go out and ask 50,000 people what they think? What's the typical number? 2,000, 3,000. Huh? Unless you're doing polls among EECS and LNS students in the department and you want to veer it in a particular direction, then you go and strategically choose the people you ask. Okay. Well, this is a ridiculous number. Ridiculous. Psh, Chevy Chev. I don't understand how he became famous. So we need a better bound. What's one of the things we can do to make this bound better? In typical polls, is the accuracy 1%? What is it usually? 8? Oh, there are some that are 8, but typically it's like 3%, right? So what happens if I change my accuracy to 3%? So here's my question. What if we relax the accuracy requirement? So instead of 1%, we now allow 3%. Allow 3%. How is that going to manifest itself in your expressions? Let's go here. Notice this becomes, so let me just rewrite. This becomes 0.03. This becomes 0.03 squared. Can you predict how it's going to affect the final n? I reduced the accuracy by a factor of 3. How is that going to reduce the number of people I have to poll? Factor of 9. That's exactly what's going to happen. By simply relaxing the accuracy requirement from 1% to 3%, I am going to reduce the number of people that I have to go and poll by a factor of 9. So I'm going to let you work this out because I want to get to the central limit theorem. This reduces the minimum n by a factor of 9. So we go from 50,000 to 50,000 over 9, whatever that is. What is that? 5,000 what? 5,600? Yeah, 550, yeah, 5,556. Still too large. We can do better. Keep hope alive. Okay. So, now comes a 1-minute break. And then I'm going to talk about the central limit theorem. Okay. Before I start talking about the central limit theorem and what it means and how we can use it in the Polster problem, among many other things, I want to talk to you about a spiffy trick that we can use to standardize any random variable that has a finite mean and finite variance. So let's say I have a random variable x. It's got a mean of e of x and some variance sigma x squared. Okay? I can construct a random variable z by subtracting from x its mean. What happens when I subtract the mean of a random variable from itself? What kind of random variable do I get? A zero mean random variable. So subtracting the mean gets rid of that bias due to the mean. And I divide by sigma x squared. I'm sorry, not sigma x squared, sigma x. So I subtract the mean and divide, these are the two things I do, and divide by the standard dev. The mean of z, you just told me, is 0, because the sigma x comes out. I have the mean of x minus its mean, linearity of expectation, I get 0. What is the variance of z? It's 1. Because it's 1 over sigma squared times the variance of x minus e of x. And when you subtract some constant from a random variable, in this case that constant happens to be the mean of the random variable, but it doesn't have to be. When you subtract a mean from a constant amount from a random variable, do you change its variance? We talked about this before. So this is also sigma x squared, and the product of the two is 1, which means that the standard deviation of z is also 1. Any random variable that has 0 mean and unit standard deviation or variance is called a standard random variable. And all of these random variables will form a family where they all follow, their PDFs or PMFs follow the same general shape, but with different means and variances. But there's a monarch in that family, and that monarch is the 0 mean unit variance version of that, or representative of that family. This is very important because when it comes to the Gaussian, all we have is the table for the standard Gaussian. And so we have to be able to convert any other Gaussian to the standard Gaussian before we can proceed. Yeah? There's no closed form? Yeah, I think it's been proven that it does not have a closed form. Yeah, we can talk about finding a reference for it later. All right. So, what does the central limit theorem say? The CLT. We again have our random variables x1 through xn, which are IID, and each has a mean x e of x, and, well, I'll call this mu because now we're going to have too much clutter. They have mean mu and variance sigma squared. Okay? And we're going to assume that mu and sigma squared are finite. Define the random variable Zn as the sample mean minus mu divided by the square root of the variance of Mn. Remember, Mn is the sample mean. What was the mean of the sample mean? If all of these xi's are identically distributed? Huh? Mu. You said it's unbiased. And the variance of Mn is sigma squared over n. We determined these before. So, what have I done here? What is Zn? What's its mean? What is the mean of Zn? 0, because I took the random variable Mn, subtracted the mean, and so that's why it's a 0 mean random variable. And then I've also divided by its standard deviation. I've divided by the standard deviation of Mn. So what have I done? Why is this a tricky question? Variance of Zn is what? 1. I just standardized it. Didn't we just talk about standardization? My random variable of interest in this particular case happens to be the sample mean, not just some arbitrary random variable. So, Zn is the standardized version of Mn. It's got 0 mean, unit variance. The central limit theorem says the following. The CLT. The limit as n goes to infinity of the distribution, cumulative distribution function for Zn approaches the Gaussian CDF, which is given by this. Standard Gaussian CDF. This is what we said does not have a closed form expression. Now, this is subtle. In many cases, not only does the CDF of these sample means approach that of a Gaussian, but in fact, their individual PMFs also approach the PDF of, or their individual probability laws approach that of a Gaussian. So let me switch screens a bit. We're not going to prove the CLT in this class. That's not the point. And if you want to do that, you take a math course. So let's see. It's missing. So how do I? So let's start here. I've stolen these from my colleague John Tsitsiklis at MIT, whose course I taught while I was on sabbatical there. So notice here, this is a uniform PMF. Okay? Random variable k, each ki. I add 2 of them. The PMF for the sum of these 2, if they're independent, becomes a triangle. If I add 4 of them, notice it's beginning to take on that bell-shaped curve. And if I add, I think here, 32 of them, notice it looks very nicely like a Gaussian. So this is an example where not just the CDF of the random variable, but in fact the PMF of the random variable approaches that of a Gaussian envelope. And then the example below, the 4 blocks below, start with an exponential. If I add 8 of those exponentials, I get this shape here. If I add 16 of them, I get this shape here for the PMF. And if I add, I think the last one is 32, I get my nice bell-shaped curve. Okay? Now, this doesn't always happen in such a happy, nice way. Sometimes the probability law is weird enough that as you keep increasing the number of terms that you add, you don't get that bell-shaped curve. Look at these spikes. These spikes are just going to be there. But even for these ugly ones, the CDFs converge to the CDF of a Gaussian. So the smooth curve, or whatever is the smoothest curve here, is the CDF of a Gaussian. Notice it crosses the 1/2 mark at 0. Okay? Which represents the symmetry. So even though the PMFs don't converge to a Gaussian envelope, the CDF, if I keep adding these lollipops from the left up to a certain point and figure out the CDF of the discrete random variable, it approaches that of the Gaussian. And this approach is pointwise. So let me switch back to this approach is pointwise convergence. Is it showing up? Yeah. So qualitatively, for a lot of the probability, for a lot of the random variables that we've studied, the PMF or the PDF does approach that of a Gaussian, but that's not the statement of the CLT. The statement of the CLT is that the probability that Zn, this is the limit of the probability that Zn is less than or equal to some threshold, approaches that of the CDF of the Gaussian. So this is the CDF of the Gaussian. Okay. I think we'll have just enough time to set up the problem for the Polster problem for the CDF solution. So back to the Polster problem. Polster problem. So we have our sample mean of the people we've asked. We know that the sample mean is an unbiased estimator, so its expected value is mu. Its variance we determined was sigma squared over n. I'm going to remove the sigma subscript x from the discussion. And we're interested in finding the probability that the sample mean is away from the true mean by more than, now we're going to keep the relaxed accuracy. 3% is less than or equal to 0.05. Okay? Well, what does this mean? Can you standardize Mn? What is Zn? The way the problem is set up has taken care of half of the standardization problem because we've already subtracted the mean. So what else do I have to do? Divide by the standard deviation for Mn, which is the square root of this, sigma over square root of n. So I divide by sigma over square root of n. Are we all here? That's the standardized Mn. standardized MN. So this variable Zn has zero mean and unit standard deviation or unit variance. Okay. So when I go back to my inequality, I want to convert this to something related to Zn. So I want to look at the denominator here is non-negative, so I can keep this, and if I divide by sigma over root n, I have to do the same thing where? With the what? What do I put here? Help me out. There are people waiting outside. 0.03 divided by sigma over root n. And I want this to be less than or equal to 0.05. Okay, let's clean this up a bit. So this means the probability that Zn is greater than or equal to root n times 0.03 over sigma is less than or equal to 0.05. Right? The central limit, Zn. The central limit theorem says, says what? That the Zn CDF, well, is this, how do I convert this to a CDF? Because that's what the central limit theorem tells me. I have to convert it to a CDF. What do I do? Is this in the form of a CDF? So I have to write this as 1 minus the probability that Zn is less than or equal to root n times 0.03 over sigma is less than or equal to 0.05, which means the probability that Zn is less than or equal to root n times 0.03 over sigma is what? Greater than or equal to 0.95. Right? The CLT says this approaches what? As n increases, I can estimate this with what? Phi of no. That's not what we're... Zn approaches a Gaussian. So we have a Gaussian, and it's got a zero mean unit variance, right? And we want the probability that Zn is between where and where? This is a showstopper. We got to get out of here. What are these boundaries? Forget the dotted lines. I want the probability that Zn is between two values. What are those two values? 0.03 root n over sigma and minus 0.03 root n over sigma. I want this probability. I'm going to let you play with this over the weekend. On Tuesday, first thing I'm going to do is finish up this problem, and then we'll move on to other topics.